Hello everyone, my name is Amin Hinrani. I'm a graduate student at the Massachusetts Institute of Technology, and today I will be talking about PcDGAN, a continuous conditional diverse generative adversarial network for inverse design. The primary purpose of our work is to develop an approach for inverse design using generative adversarial networks, such that designers are able to use these tools effectively in design generation. So the primary challenge in doing something like this is dealing with fully continuous data in conditional generative adversarial networks. Another challenge is to ensure that the designs generated by these GANs cover the design space evenly, as this is necessary for effective design space exploration. And finally, in a lot of design data sets, and in fact, most continuous data sets, there are issues with sparsity in certain parts of the label space. And this is something that is also it requires addressing in doing something like this. So the primary motivation is to improve the engineering design process. So the typical engineering design process starts from a problem statement, and it's followed by idea generation, which leads to a specific number of concepts and candidate designs. And these candidate designs all have to be modeled, analyzed, constructed, and tested. And the process has to repeat iteratively multiple times until a sufficient number of candidates exist and the best candidate can be found. This can be very tedious and time consuming, and both computationally and uh, economically expensive for designers. So this aspect of design synthesis and design space exploration requires a lot of attention, and improving this can be very valuable for designers. The typical approach for improving this is to avoid the iterative part, and for that, the inverse design approach is introduced. Now, in the inverse design problem, what we're doing is we're integrating our design requirements into the design generation process from the start. In doing this, we start with our requirements in a specific design domain and move to generate designs using an automated design generation optimization approach. And the candidates that come out of these tools are typically highly likely to meet those specific requirements, or they are actually guaranteed to meet those specific requirements. And this makes the modeling and analysis and construction of designs and testing only necessary once. It removes the iterative part and can make the process much more efficient because, again, those designs are highly likely in meeting those requirements from the start. So the most important aspect of this is the inverse design generation tool and this automated design generation tool. Now, there's two things that are very important for designers when using these tools. The first is that the designs generated by these tools must cover the design space evenly. And this is because effective design space exploration requires a complete picture of what is possible given these requirements. And this is very important when it comes to generating designs and exploring different possibilities in generating engineering design. And the other part, obviously, is to meet specific requirements that we set out to meet using the inverse design approach. So these two are the pivotal points that we're trying to address using data-driven approaches such as generative adversarial networks. So the typical generative adversarial network process starts from a discriminator and a generator. And the discriminator in the GAN learns to decipher between the real data and the generated data, while the generator tries to fool this discriminator into thinking generated data is real. After training and after a lot of iterations, the generator is hopefully able to map a latent space into the design space, which effectively allows it to generate a lot of designs nearly instantly. However, in this bare-bone configuration, the generative adversarial network does not really present an avenue for effective inverse design, as we're not able to incorporate our design requirements into this generation process. And this is where conditional generative adversarial networks come into play, where now instead of the generator learning the distribution of the data, it also learns the distribution of the data and the performance. So hopefully it'll be able to map a latent space as well as a desired performance into designs that meet that specific performance requirement. However, there are some limitations in the typical conventional conditional generative adversarial network. The first of these is that these models were designed for classification labels and images originally. However, in design, labels are fully continuous, and this creates a huge problem when it comes to dealing with continuous labels. Another problem the GANs in general face is this lack of diversity and sometimes mode collapse. So this is another issue that designers really think about when using these kinds of data-driven approaches, is that can they be ensured that the design space is covered fully by the generated samples. And in many cases, GANs suffer from the lack of diversity and mode collapse, which can be problematic for using these approaches for inverse design. So we set out to address all of these problems in our PcDGAN architecture. So we changed the architecture of the conditional GAN slightly and add an estimator-based conditioning as well as the conditional generative adversarial network so that they can complement each other and improve conditioning and also deal with continuous labels. So how do we deal with this? How do we move forward in meeting specific requirements? So instead of applying the typical empirical loss that GANs have for conditioning, we instead move towards a singular vicinal loss, or more importantly here, we're talking about the vicinal loss. Now, the vicinal loss is basically a sampling during training in the vicinity of a desired label rather than exactly at the desired label. So, for example, in many cases in continuous spaces, and in fact, this is a specific property of continuous spaces that when a specific label is required during training, for example, if we're training and we pick a specific label within the label space, there may be no samples associated with that specific label. And because, the nature of the continuous data. But by sampling in the vicinity, we're able to get some samples for that specific label, and we're able to train the discriminator and thereby the generator in generating designs not necessarily at that label, because in continuous sense it is nearly impossible to meet a very specific value in a continuous space, but rather generate samples in that vicinity, which would be effective for design synthesis and inverse design. So the reason we're using the vicinal approach is that it gives us an approach to deal with these kinds of sparsities, where there's no data or there's a small amount of data. And also, one of the benefits of using this over the conventional type of approach, which we saw in cGANs, is that we're able to generate designs based on the vicinity of a specific label, which avoids the problems with the empirical loss, which requires a large number of samples for every given label. So in a classification sense, this would not be a problem requiring a large number of samples for every label, because there'll probably be a large number of the data points available for each of the classification labels. However, in continuous data, as we discussed, this is not practical. So having that vicinal loss helps us deal with that. And this is, again, a problem that broadly exists in engineering design data sets and also most continuous data as well. So by doing this, we're able to address the issues of cGAN. And then finally, we have the Lambert log exponential transition score, which we'll talk about later. And this is something that we incorporate into improving conditioning beyond the vicinal loss. So the next aspect of the effective design tool was generating design samples that are diverse and cover the design space evenly. For this, we introduced this DPP kernel and the DPP loss. What DPP means is the determinantal point processes. These are processes that come up in quantum mechanics, and they basically allow us to probabilistically model diversity. And given a set of samples, using the DPP kernel, we're able to determine how diverse the set of samples is. So another benefit of using this determinantal point process is that we can actually model diversity and quality simultaneously. And these are sometimes competing concepts, where increased diversity may lead to worse conditioning. And this is something we're trying to incorporate into the same loss function, so that not only is our diversity now fighting against meeting specific conditions, but also helping it. So the way we do this is by constructing a DPP kernel as described here. So for every entry in the DPP matrix, we have the K term, which determines the similarity between two samples here in I and J. And the similarity can be measured using any similarity metric. We use the RBF kernel in our application. And then the other term that we apply to the DPP kernel is the quality term. Now, the quality of each sample will also be multiplied to this. And by doing this, we are basically combining meeting increasing quality as well as diversity at the same time without them becoming separate competing entities in the losses. And finally, the loss would be basically the negative log determinant of the DPP kernel. Now, how do we determine the quality of meeting a specific condition for samples? Now, that's where the Lambert log exponential transition score comes into play. Now, this score has a few properties that help us employ it in the DPP kernel appropriately. So one of the things is that it measures how well a specific sample meets a condition. And the way it does that, it uses the estimator's prediction, and it also uses the input condition. So having the input condition and the predicted actual performance, we can measure the difference, and using that, we can give every sample a score and how well it's meeting a specific condition. And the way we calculate it is using this equation you can see here, basically inputting the difference between the requested condition from the generator and the estimated actual performance. And there's a hyperparameter, the Lambert cutoff, which determines how aggressive the gradient of this function works, and also where the other part of this comes into play, which is that it has a self-reinforcing property. Now, in GANs, it's been shown that giving more weight to samples with desirable features leads the GANs to generate those kinds of samples with more desirable features. So here, what we're trying to do is we're trying to build that into this Lambert log exponential score. And we do this in this way. As you can see here in this animation, the purple curve shows the Lambert log exponential itself, and the red curve shows the gradient of the Lambert log exponential. And as you can see here, we're changing the Lambert cutoff hyperparameter. But what you can see is that the gradient is higher near the point of 0, which is perfectly meeting the condition, which is a desirable feature, as we want the training to focus more on samples that are close to meeting rather than samples that are very far from meeting a specific condition. And also has another feature that the gradient stabilizes very quickly near 0, which is something else that is important, as we don't want the GAN to be thrown off when it's actually meeting the conditions well. So we want a stabilizing region once samples are being generated in the right spot. The gradient is stabilizing the training and not throwing the GAN off. And so finally, we like to achieve diversity regardless of condition and across the label space. And for this, what we do is we take a singular approach in sampling. And the reason we do this is it's going to be very evident in a graphic. I'm going to show you why we do this. So the thing is, we want diversity to be promoted everywhere in the label space. So regardless of what condition we give to the generator, we would like the generated samples to cover the design space evenly. And for this, we use the singular sampling, which ensures the DPP loss is applied to every single condition separately. Now, visually, let's take an example of a performance space like this. These 5 points that I'm showing you here are fairly diverse in terms of how far away they are from each other and how well they cover the space. However, if this specific GAN was generating samples for, say, a condition of 0.95 only in the specific region that I'm highlighting right now, by sampling in a non-singular way, the model will never be incentivized to move away from this if this collapse has happened, because other samples that are being applied at different conditions are going to be in different locations, and the overall diversity of every batch will still be high. But by sampling singularly, only sampling one condition at every batch during training, we ensure this kind of collapse cannot happen. So finally, we test our method using a few case studies. Now, the first case study is a simulated case where we artificially generate this kind of data, one uniformly distributed, which is a very typical case, and the other one, an imbalanced data, basically testing how diverse the samples generated by the model is going to be, and how well it's going to cover the design space, basically challenging diversity in the second example. So the first example, what we see is that in the likelihood score, which measures the probability of meeting a specific condition given the distribution of the generated samples, we see that PcDGAN has a much better likelihood compared to the state-of-the-art CcGAN, has a lower label error compared to the state-of-the-art CcGAN, which is the average error or the mean absolute error of the generated samples and the desired condition. And finally, the diversity here in the evenly distributed case, we see that CcGAN has actually done fairly well, and the diversity is on par. However, When we move to the uneven distribution of data, we see similar trends in the likelihood and label error. However, we see there's a clear difference in diversity now. Because the data was heavily imbalanced in a specific mode, it seems CcGAN has actually failed to do this properly. And we can visually confirm that this is the case. As you can see here, PcDGAN has been able to condition properly across the label space and also generate samples over the entire design space, while CcGAN has collapsed mostly to one of the modes, and the samples being generated on the other modes are not meeting the specific condition, which in this case is a condition of 0.4. And clearly, only the samples in the dominant mode are meeting the input condition properly, and the rest are not, while in PcDGAN we see the opposite picture, basically. The other case is a real-world example of inverse airfoil design, and what we're trying to do here is create an inverse design tool for a given lift-to-drag ratio. So given a lift-to-drag ratio on an airfoil, we would like to generate candidates that meet that specific requirement. Here you can see the distribution of the lift to drag on the airfoils in the right-hand side figure. What you see here is that there are sparse regions in the data set as highlighted with the red markers here. And these sparse regions can create a lot of problems for sample selection, and we'll get to those, the potential problems later. And so the singularly sampling also helps with this. So again, similar trends are seen: high diversity, lower label error, and much better likelihood in this case as well compared to the state of the art, which again shows how effective PcDGAN can be at just meeting specific requirements, but also maintaining diversity, basically doing the two primary things that we need from a design tool simultaneously. And here I want to just show how the likelihoods are different. So we see that the likelihood values are much higher for PcDGAN, but visualizing this by looking at the distribution is also possible. So I would encourage the audience to look at CcGAN's distribution as the condition moves from the left to right, and you can see the distribution does not smoothly move across, and this is basically what causes the likelihood scores to be lower. And now I'm going to repeat this, and you can look at the distribution of PcDGAN moving very smoothly and evenly across without much error, which is actually the reason why it's so much better at meeting having a much better likelihood of meeting specific conditions. And finally, we can visualize the diversity as well. It's clear that PcDGAN covers the design space more evenly, while CcGAN closely mimics the data set, which are indicated by the orange dots. And this basically visually proves that that difference in diversity is actually something that is measurable. So these distributions of the TSNE of the airfoils show that the diversity loss is doing what is expected to do. And finally, as we said, the sparsity problem comes into play where there are few samples at the extreme. So for example, here we have an input label that's very low on the low end of the condition space. What we see is that CcGAN has failed to generate high quality samples with the trailing edge of the airfoil being open, which is physically invalid. This is something we address with our singular sample selection as well, because we select labels not based on the data, but rather uniformly across the label space. And by doing this, we are able to avoid these low quality samples to some extent. And finally, it's important to mention the limitations. So clearly using a neural network-based estimator can be flawed because it may not translate to real-world performance. And this is something that we intend to address in the future by improving estimators and coming up with ways to quantify uncertainty in the estimator to build that into the model. The other part is that we only had demonstrated for the airfoil case in a 2D example, but PcDGAN is a general architecture which in the future can be applied to different domains such as image generation. And PcDGAN has a huge limitation that it can only be applied to a single objective inverse design. However, in most cases in engineering design, there are multiple objectives that need to be met, and this is something that also has to be done in the future. Thank you for your time, and I hope to talk to you soon, and I look forward to your future correspondence. Also, the code and the dataset for the project has been made public, and you can find that in the project page at decode.mit.edu/projects/PcDGAN.